Let's begin today's session. So we were discussing about thermal conduction and the concept of heat current and thermal resistance in the last lecture. And we had also seen some examples of how to calculate thermal resistance in case we have to use integration by the application of definite integration. So let's continue with that section today. Okay, so today we will start with an example wherein we have something like this. We have a spherical shell made of heat conducting material like a thick metallic spherical shell. It has inner radius A and outer radius B. Now suppose we maintain the inside at a different temperature and the outside is at a different temperature. Then there will be heat current coming out radially, okay, from the inner part to the outer part. So we have to find the thermal resistance for that. So this is a metallic spherical shell. So the metal has isotropic conductivity, say K, inner radius A and outer radius B. So we have to calculate the thermal resistance for heat flow when for radial conduction of heat. Okay. So for example, here if T1 is greater than T2, that means heat conducts radially outwards. Okay. So in that situation, what will be the thermal resistance? Is what we have to calculate over here. Okay. So this is like a little bit like the situation we had discussed in the last lecture of the frustum shaped object. We see that if you have this frustum shaped object and heat is flowing from one side to the other side like this, the problem is we cannot use the formula L upon Ka directly because area of cross section is not same, not uniform everywhere. So instead we have to use integration like this, where we chop this into differential lengths. So it's a little bit like this. Okay, we have to calculate this. We have to use integration, because the area across which the heat current flows is not uniform. Okay. You can see that the surface area at the inner surface is equal to 4 pi a square. The surface area at the outer surface is equal to 4 pi b square. So that means the area is continuously varying between 4 pi a square and 4 pi b square. Okay, so just based on this, try this out now. Try to understand how we will take the differential elements. Okay, so let's go over this concept once more. First of all, let's go over the concept of thermal resistance and heat current. So we will come back to this integration example. First, let's understand the concept of thermal resistance and heat current. So if we have for an isotropic conductor with uniform cross section, we had seen that at steady state, if we subject it to a temperature difference across the ends, then at steady state there is heat conduction that happens in such a way that the rate of conduction delta Q by delta T is equal to Ka by L into temperature difference. So this equation can be interpreted in such a way that heat current is equal to temperature difference divided by thermal resistance, where this quantity is referred to as heat current, just like we have electrical current in case of electrical resistance. And thermal resistance, if you compare the two formulae, is L upon Ka. This is called thermal resistance. So basically, this is comparable to a situation of electric current, where if you have a metallic conductor, but electrical conduction, and you subject it to a voltage difference such that this is V1, this is V2. So the electrical current that passes through is the potential difference divided by electrical resistance. Here the electric current is rate of charge flow, and the electrical resistance is rho L by A, or L upon sigma A, where sigma is electrical conductivity. Okay. So this is how we draw a comparison between the process of heat conduction and the process of electrical conduction. This formula of electrical conduction becomes analogous to this formula of heat conduction, and this relation for thermal resistance, this becomes analogous to this relation for electrical resistance. So just make a note of this concept first. We will come back to that question of the spherical conductor. Yes, so it becomes a comparable situation. Okay, so what we can say is that this situation can be likened to this, that thermal resistance is the property which tells you that when you have a temperature difference across a heat conductor, what is the rate at which the heat conduction is happening. Okay. Just like the electrical resistance is the property that tells you that when you create a potential difference across an electrical conductor, what is the rate at which electrical conduction happens. So the main use of this thermal conduction formula or this thermal resistance formula is when we consider combination of conductors. Okay. So for example, we had seen a situation where there was a series combination of conductors, but we had solved that by just a normal equation without considering any equivalent circuit or anything like that. Today, let's revisit a problem of that type. Okay, so suppose we have this kind of a combination, two different metals, A2, length L2, and area of cross section A2, whereas this one is K1 of length L1 and area of cross section A1. Okay. And what we have done is we've insulated all this from outside. So heat flows only across the length axis of both the conductors. So this is some kind of insulation. Okay. So in this situation now, if we created a temperature gradient, then there will be heat flow across the combination of conductors. So suppose we create a temperature gradient like this, or this time we can just call the temperature at this end as TA and the temperature at this end as TB. So given TA is greater than TB, find equivalent thermal resistance for the combination. Second, the net rate of flow of heat at steady state. Okay. And the temperature of the junction at steady state. So we can do this by equivalent circuit method. So now that we have learned the concept of thermal resistance, we can convert this to a equivalent circuit. Heat circuit. Okay. So we can say that we are maintaining these two ends. So there will be some common heat current that flows across them. Okay. So this is further equivalent to a single series resistor, which will be R1 plus R2, which is connected across the same temperature gradient or temperature difference. So it conducts the same amount of heat. Okay, and now we can just apply the formula. So we can see that R1 is L1 upon K1A, R2 is L2 upon K2A2. So equivalent thermal resistance will be R1 plus R2 because it's a series combination. Okay. So equivalent thermal resistance will be given by this formula. This becomes the answer to the first part, and therefore the thermal current will be the temperature difference divided by the equivalent resistance. So this will become the answer to the second part. The net rate of heat flow through the combination will be this temperature difference divided by this. Okay, and for the temperature of the junction, third part, we can see that for R1 we have the equation Ta minus T upon R1 is equal to the thermal current. So Ta minus T upon L1 by K1A is equal to Ta minus Tb divided by L1 upon K1A plus L2 upon K2 A2. Here also it should all be A1 and A2 separate areas. So anyway, so from this we will get the unknown temperature T. So this becomes the solution for the third part of the question. Okay. Okay, so I hope this concept of series combination is clear. Now likewise, we can have parallel combination also. So for example, don't worry, we'll come back to that question later. Suppose we have two different thermal conductors which are kept across the same set of temperature reservoirs. Okay. And they are insulated from outside. Now in this particular case, they have to be of the same length, but they can have different areas of cross section and different, they can be made of different materials. So their thermal conductivity can be different. K1 length L and some area A1. And this is, let's say, K2, same length L but made of some different area A2. So now what will happen is that there will be heat flowing in this direction also and this direction also. So the net current will be equal to the sum of heat flowing in the first rod. That is delta Q by delta T for the first rod plus delta Q by delta T for the second rod. That will be equal to the net rate of heat flow. Okay. So this can be now converted into an equivalent circuit diagram where the two heat resistors are connected in parallel across the same temperature difference. So this net current splits into this. So I1 is equal to T1 minus T2 divided by R1. I2 is equal to T1 minus T2 divided by R2, where R1 is L1 upon, or rather in this case, common length, so L upon K1 A1, and R2 is that same length but divided by different K into different area. Okay. So now if we just implement this conservation of heat equation over here, that I net, which is the net rate of heat conduction, is the sum of the conduction in two of them. So it is T1 minus T2 into 1 by R1 plus 1 by R. So we can see that the net heat current is temperature difference divided by equivalent resistance. So we get the formula which we know from electricity formula before, current electricity earlier, that in parallel combination, the reciprocal of the equivalent resistance is the sum of the reciprocals. So 1 by R equivalent is summation 1 by R for the resistors in parallel. In this case, it becomes K1 A1 divided by L plus K2 A2 divided by L. That is 1 upon R equivalent. Okay, so we make a note of this also. These are the two individual type of combination of resistors. Okay, so next up, let's look at an example with the application of this concept. So this is a very common type of example at the heat conduction level. So for example, we have a situation like this. There are, let's say, three identical metallic heat conductors connected like this. So these are all of length L each and made of material of conductivity K1. Okay, and have area of cross section A1 each. Now we have another material and we have three other rods made of that material. So this material has conductivity K2, area of cross section A2, and this part has length L by 2. And this point here is kept at some temperature TA. This point is kept at some temperature TB. So let's say this is minus 50 degrees C and this is 150 degrees C. So this is a combination of 6 rods insulated from the outside. Such that the 6 metallic rods. K1 is, let us say, 120 watts per meter Kelvin. Oh, before I forget one thing, the unit of thermal resistance, SI unit for thermal resistance is Kelvin per watt. Okay. Because we have this relation, heat current is equal to temperature difference divided by thermal resistance. So here heat current is in watts and temperature difference in SI unit is in kelvins. So that's how we get thermal resistance in Kelvin per watt. Okay. So K1 is given as this, E1 is given as, let's say, 6 centimeter square, okay. And L is, say, 4 meters. Whereas K2 is given as 200 watts per meter Kelvin. And this area is 5 centimeters square. Okay. So now we want to find the net rate of heat conduction delta Q by delta T across the points A and B at steady state. Okay. So A is this point here, B is this point here. And let's say we have got another point C over here. So we also want to find the temperature at the point C at steady state. Okay. So realize that when we use the concept of thermal circuit, this is a very easy problem to solve ultimately. You have to just convert this to an equivalent circuit diagram and use the concept of series and parallel combination, both of them in the same situation here. Okay. And then reduce it to a single equivalent resistance by using the combination formula, and from that find out the heat current. And similarly, by applying the equivalent Ohm's law across each of the conductors, we can find the temperature at each of the corner points. So in this case, we have to find the temperature across at the corner point C. Okay, so just try to convert this into a circuit first. Yeah, Ohm's law is the electrical current across a resistor is related to the voltage difference, like this. Okay. So the equivalent of Ohm's law for heat circuits becomes that this is the temperature difference divided by the thermal resistance. Okay, so let us look at the equivalent circuit concept now. So for equivalent circuit, what I will do is, first of all, I will name these other points also. Okay. Now, these three resistors are R1 and the other resistors are 2R2. So this is also 2R2. The length is half, so the resistance will become double. So here we can calculate R1, R2, and 2R2 is, sorry, this will be R2 by 2. Length is half. Okay, so let's calculate these values. So 4 meters, 120 and 6 centimeters square. Okay. Now we can start reducing the equivalent circuit. So first thing we can see is that this is a series combination. So this will become R1 plus R2 by 2 plus R2 by 2. So we can convert this to an R equal to this much. Okay. So whatever current I is over here, same current I would be here. And if this current is splitting here into some current I1 and I2, so this current is again splitting into I1 and I2 over here. Okay, so next step we will take parallel combination of these two. So this becomes equivalent to, let's say, R prime, which is R in parallel with R2. So that will become, calculate that value. It's R2 by 2 second, because the length is half. No? So see, in this original diagram, you can see that these resistors have half the length. So, oh sorry, yeah, this should be R2 by 2. In the diagram, I've made the correction. In the, so anyhow, coming back to this becomes, so we can do an approximation of this. This will be about 28.2 Kelvin per watt. This R prime will be. Similarly, this will be, okay. So now finally, the equivalent resistance here would be R1 plus R prime plus R1. Okay. So that would work out to be, this much. नहीं नहीं, अरे समर्थ, it's like this. What is happening now in this part? See, the same current is going through these three resistors. So they are in series. So if these resistors are, let's say, R1, R2, and R3, so in this equivalent diagram, these three are in series. You're understanding? They're not in parallel. So this R prime is R1 plus R2 plus R3. Understanding now? And then these two are in parallel. Okay, so that's what we have done over here. First, we have made the series combination of these three, ED, DC, and CF. Okay. So that's how we have got this R from the series combination. Then this R and R2 are in parallel. So we got this R prime from the parallel combination to be. Okay. And then we are getting the equivalent resistance of the whole combination like this. Okay. So now the net heat across the points A and B is this temperature difference divided by the equivalent thermal resistance. Okay. Yeah, Shikhar. So the thing is, see, we convert this to an equivalent circuit like this. In that, we first, combine these three for series combination. So it becomes this diagram below. Okay. Then we take the parallel combination of this and this. So it further becomes this diagram below. And finally, is the series combination of these three. So the equivalent resistance is this much. Then just divide the temperature difference Ta minus Tb by the equivalent resistance, and that's it. We have found the this thing. Okay. Now we'll come back to the integration examples that we were doing earlier. So next thing is, if you have to apply integration, so in what situation we have to apply integration? Let's understand that first. Yeah, Durgesh, to find the temperature at the point C, you have to just use the normal circuit concepts. So because it's going to take some time to calculate, so I'm not getting into that fully. Okay, but how you will do it, I'll tell you. To find the temperature at the point C, now we had named all these other points also. So first, what you do is you find, see, you know the current through this resistor. So by using Ohm's law equivalent for FD, you find the temperature at the point F. This resistor was R1. Okay. So from this you find the temperature at the point F. Okay. Then what you do next step? This is the complicated step. You find I1 and I2. Okay. So you find I1 and I2 from the fact that I1 plus I2 is equal to I, and I1 is to I2 will be inverse of this ratio of resistance. So this was R2. Okay. This was 2R2 to R2. This was R1.
Sir, R2 by 2.
So it will be inverse of, so this combination we are taken as R. So this R was R1 plus R2. So this ratio will be inverse of this. It will be R2 is to R. So from this you find out how much I1 is. Okay. And once you found I1, then you apply Ohm's law across CF. So you have TC minus TF divided by 2R2 is equal to I1. And from this you find out how much TC is. Okay. So this is the general method, but we have some odd values here. So I'm just saving time and not doing the full calculation. You find many questions of this type in the H.C. Verma chapter of heat transfer. Okay. Now let's come back to this thing, the application of integration. So for example, we can have, first of all, in a situation where the conductor is isotropic, that is K is uniform, okay, but area of cross section is not uniform, okay. So an example of that was the spherical shell example that we were doing earlier today. So this is a solid metallic sphere, I mean solid metallic shell, thick kind of shell. It has thermal conductivity K, inner radius A and outer radius B. Now if we've kept the inside at temperature T1 and the outside at temperature T2, then heat will flow out radially like this. This is the direction of heat flow. So to find out the equivalent thermal resistance here, what we have to do is we have to slice this into shells, thin spherical shells, like you did for calculation of moment of inertia, etc. Same way, so whenever you have a spherical body and you are calculating something across its volume, this is the procedure used. So you take a shell of radius r and thickness dr. So for this thin shell, which has radius r, thickness dr, and surface area how much? 4 pi r square. So the thermal resistance, because it's a differential shell, so we'll write it like this. It is going to be dr upon Ka, or dr upon K into 4 pi r square. Okay. So now if you see all these shells, they are in series combination with each other, one after the other, because the same amount of current is going through them. Okay. So the equivalent thermal resistance of the metallic spherical shell will become integration or summation by integration for series combination of all shells from r equal to A to r equal to B. So become integration of dr upon 4 pi k r square from r equal to A to r equal to B. So this becomes the thermal resistance. Okay. So now in this case, you can see that the net rate of heat flow will become the temperature difference between the inside and outside divided by this thermal resistance, where this thermal resistance is a function of the geometry, that is A and B, and also the thermal conductivity of the material. Yeah, thermal resistance part is part of tomorrow's exam. So make sure for tomorrow's exam you are clear with this formula of thermal resistance for an isotropic conductor of uniform cross section like this. Okay. Then series combination, equivalent thermal resistance is summation of resistances that you connect in series. Parallel combination, inverse is summation of reciprocal. Okay. And these couple of cases of application of integration. Okay. Now we'll look at one more example of application of integration. So another situation that can happen is in case of a conductor with non-uniform thermal conductivity. This type of conductor is called anisotropic, the opposite of isotropic. Yeah, I'll show you the steps of the previous question. So this is just integration. Okay, we are just putting the limits in the integration. It's an integration of this type. So you just put this over here, this integration. Okay, you will get this answer finally. Okay, so another type of situation in which we use integration is something where our conductor is anisotropic. So the thermal conductivity itself is varying. So in such type of question, the value of thermal conductivity, how it is varying, will be given to you in the question. So for example, we have, let's say, a cylindrical conductor. I'll just take another 5 to 10 minutes to complete this part. Yeah, some relation will be given. Okay, that's correct. So suppose we have a cylindrical rod of length L and radius A or whatever. Okay, so cylinder, solid cylinder of length L, radius A, but with anisotropic material such that it is given that the thermal conductivity is a function of x. So inside the rod or cylinder, if x is the distance of a point from the left end, then the thermal conductivity at that point is equal to, let us say, given to us k naught into some factor, like it is, let's say, it's like this, where k naught is a constant, but x is the position of a point with respect to the left end of the rod. So now we want to find the equivalent thermal resistance. Okay. So as you might have guessed, we will slice this rod into small discs because we can't take the formula L upon K. K is variable. But if we have a thin disc of thickness dx, so within that disc we can take a uniform value of K. Okay. So what we'll do is here we'll slice a disc like this, let's say, of thickness dx. So this thin disc we can now calculate its thermal conductivity. So for a differential disc, okay, which has thickness dx, thermal conductivity equal to K naught L upon L plus X. Okay. And this thing, area pi a square. So for this, what happens? The differential thermal resistance is dx upon Ka. So that becomes dx upon K naught L upon L plus X into pi a square. So it becomes quite an easy function to integrate when we are going to come to that. Okay. So now these are all in series combination. So equivalent thermal resistance of the entire cylinder will become series combination. So integration of this thing from x equal to 0 to x equal to L. Okay. So you can see it's a very simple integration. Only x is the variable, everything else is a constant here. So it's we are integrating a linear function of x, so it will become a quadratic function when we take the indefinite integration and then put the limits. So that will give us a thermal resistance. Okay, so the question has to give us the value of how k is varying with x, like this. Okay, but once that is given, we just have to convert this to an integration. So you can see that this all constant comes outside. And it's a very simple integration of this. Yes, that's correct. This will become 3 by 2 L square, but multiplied by this factor. So finally our answer will become 3 by 2 L upon K naught into pi a square. This will be our thermal resistance. Okay. So if we subject this to a temperature difference like this, then the thermal current through this will become T1 minus T2 upon this. So it will become 2 times K naught into pi a square by 3L into T1 minus T2. This will be the steady state heat current. Okay, so hope these couple of examples with application of integration are clear. Okay. So yes, this is going to be part of your test syllabus tomorrow. So make sure you revise today's lectures questions once very carefully. But moreover, what is more important for tomorrow's test is going to be the applications of first law of thermodynamics, including heat engines, cyclic processes, polytropic process, all that, and also the part of heat before that, that is calorimetry and this thing, thermal expansion. Okay. And of course, it being a common test, so make sure you do revision from work, energy, friction, etc. also once. Just go over the various techniques of solving problems because those chapters will also be coming. Okay. So that's it for today's session, people. Wish you all the best.
Thank you, sir. Bye, sir.
Okay, people.
Bye,
Bye.
sir. Thank you, sir.
Thank you, sir. Bye.